Welcome to PyData Jeddah webinar. I'm Yasmin Al-Saadi, and here with me Afnan Al-Shahri and Hassan Al-Sawadi. And from behind the scenes, Abdul Ilah Al-Misfir, Najla Al-Baz, Haya Al-Matari, and Renanda Al-Urri, the PyData Jeddah team. This is our fourth webinar, and we are getting better in doing this, so yay. Today we have a special speaker, actually a colleague from another PyData chapter. He is the co-chair of PyData Amsterdam, and he will talk about Bayesian hierarchical time series analysis with Prophet and PyMCA3. So, Matthias, the mic is yours.
Right. Awesome. Thanks. I'll share my screen as well. Right. So you should be able to see my slides now, right?
Yes.
Cool. Awesome. All right. Yeah. So thanks for that introduction. Indeed, my name is Matthias. I am indeed the data science lead at. Whoops, it's a bit slow. Yeah, I'm indeed the data science lead at Accelerated. And at work, I've been responsible for training, educating, and developing over 50 junior media data scientists in all kinds of different topics. And actually, the stuff that I'm about to present to you today is also something that sort of came out of this training and out of some of the work I've seen these accelerators do at clients, and me thinking that there had to be a better way to solve their issues. As you said, I'm also indeed actively involved in two other chapters of PyData, both the PyData Amsterdam conference and meetup, as well as the PyData Global virtual conference from this year, November 11th till 15th. Apart from that, I like to do open source stuff. So I maintain a project called Scikit-Lego, which is a library that just contains like things that we found to be useful over the years when building scikit-learn models. And I recently started this time series thing. About PyData Global, I do want to plug the event a bit. Tickets are on sale at the moment, and the program is announced. Tickets are pay what you want. So it's accessible to as many people as possible. We have like more than 70 talks, I think, and like a dozen tutorials, a bunch of short talks, and some extracurriculars. So it should be a lot of fun. But that's not what we're going to be talking about here today. Today, I would like to discuss with you a specific type of time series problem, and namely a business time series forecasting problem. Because forecasting is one of those things that you just happen to do as data scientists in a lot of organizations. Because it's very often sort of the most common input to all kinds of planning and scheduling problems. Right, stuff like workforce planning, but also capacity planning, and maybe factory expansion decisions or assembly line changeovers that need to happen. And while it's therefore very important, time series modeling can be also very tricky, especially in these business contexts, because generally your data is not super good. So what I have here is it's not real data, it's fictitious data, but it resembles sort of the patterns that you would generally see in some kind of like fast-moving consumer goods or whatever type manufacturing process. We have a bunch of products that are tracked over a certain amount of time. In this case, the longest time span is about 2 years from the start of 2018 till about now. And all these time series, they have some things in common, right? What we see some obvious yearly seasonality where we have a repeating cycle over the year where sometimes products sell more, sometimes products sell less. But there also seems to be some kind of weekly seasonality going on. There seems to be missing data, right? All these weird little spikes down to zero are probably indicative of measurement errors or just data not being collected properly. But there's also trend changes, especially like near the start of 2020. In the blue line, we see there's an obvious trend change. We have newly introduced products, like the gray, the green, the yellow ones are definitely starting later on in our time series, and some of them are even stopping early. And then there's these yellow and these orange and these blue bands sort of around here that have some kind of promotional activity or some kind of non-seasonal event that increased the sales during an amount of time. And I plotted 5 here, but in most contexts, you would actually not have just 5 of these. You would have, like, for each product, for each SKU of that product, for each region that you sell in, you kind of want to fit these time series. So very often it's more in the order of hundreds than tens. And if you try to model this with classical time series models, where you sort of try to get that generative process that made your data, then you're going to struggle, because you would end up with some kind of maybe a Serimax model, because there's the seasonality you need to capture, and then there's these autoregressive components. But generally, those seasonalities aren't meant to go back an entire year. Because basically what it does, how those models learn, is they look at what was the feature value one period of seasonality ago, and they try to learn a weight, like how much should this weigh in the prediction that I'm going to make for tomorrow. But especially for these newer products, for like orange and, yellow and green, these ones at the end here, there's no way we can look back an entire year. And like there's a bunch of these kinds of issues. Also, generally you can't really model multiple seasonalities in one go, or at least not natively. You would have to do some kind of Fourier decomposition. All these additional promotion effects are kind of hard to model. Missing data you would need to impute at the very least, or somehow remove, but you need to deal with it. And that just doesn't scale when it comes to the amount of effort that you need to do for all these 100 time series to actually be able to model them. And that's actually exactly the problem that some researchers at Facebook at some point also faced. They have a very similar situation where they have like probably tens of thousands time series they actually want to model, but not the people capacity with the time series experience to actually properly model all of those. So that's why they decided to tackle this some other way. And they came up with this thing called Prophet. And what is Prophet then? So Prophet kind of tries to do away with that entire, let's model the generative process of our data. And instead it tries to say, well, how about we just treat it as a curve fitting exercise, where we have a bunch of different components, and those components can be summed together, just sum them together to in the end produce the time series that you want to fit. And on the screen here we see 2 main components, a trend and a seasonal component, and then there's a bunch of additional regressors that you could add that could take any real shape or form that you want. It assumes the noise is then independently distributed around these predictions, because most of the trend and all the other things should be captured in one of those components. And the nice thing about this is that it, in theory, is a really flexible way to fit time series. Because if you want a slightly different way that seasonality should work according to what you think your problem domain calls for, then you should be able to say, let's grab this seasonality component, take it out, and think of a slightly different way to add that to our final predictions. And also, that entire problem that we had with missing data is not really relevant anymore, because you don't do an autoregressive model, but you do curve fitting. You simply don't look at the measurements that are missing. Don't really need to deal with those anymore. Also, the decomposition thing just makes it really nice to go back and see, like, okay, why did a certain prediction come to be? Or like, what is my model actually learning? Because you can look at the trend individually from the seasonality and from any other additional regressors. But there's some parts about Prophet that I don't think are sufficient for this problem that I'm describing to you here. And the first one is basically that Prophet, well, that flexibility that this decomposition model sort of promises isn't really realized in the way that Prophet is set up. It's not very easy for someone randomly to go in and change one component while keeping the rest without needing to sort of change the entire source code of the thing. And also, if we look carefully at this data, you might say that there isn't 5 individual seasonalities in this series. It could very well be that there's actually only one seasonal effect, but some of the products are co-seasonal and some of the products are contra-seasonal, right? So we would kind of want to be able to model that effect and be able to tell our model, like, these time series should share some of their parameters maybe. And unfortunately, the way that Prophet is set up, that's just not possible. So what I set out to do was basically to think of a way and to open source a way in which we could model these series in a more playful, interactive way while keeping into account these shared parameter spaces. And to do that, we have to first look at, okay, what does Prophet actually do when it fits a trend and when it fits a seasonality? And it turns out that those are actually relatively straightforward. The paper suggests 2 ways of dealing with the trend. One is a linear trend and one is a saturating growth. For the problems that I've been facing, the linear trend seems to perform better and seems to make more sense. So that's also the thing that I implemented up until now. And how it works is that basically you take a starting initial growth. Like, how much does our trend increase for each time step? And that's this variable k here. And in order to say that it should be possible for this trend to change over time, what the Prophet model does is it introduces regularly spaced change points. And by default, these are just like regularly spaced in your domain. If you have some domain knowledge, you could also tell it to basically put these change points at specific moments where you know something has changed. But the general gist is just make sure that there's enough of them and put a strongly regularizing prior on it to sort of shrink it down to 0 for the cases where nothing really expected to change. And the growth at a certain point in time is then basically this summation. So the growth or the trend at a certain time is the initial growth plus all the sum of all the deltas that have already passed. This sum is not super great to model though, right? If you need to write this down in a matrix way, then this summation can be tedious. So the paper actually models it slightly different. All this math, by the way, is directly from the paper. It's quite accessible and readable if you are interested in it or if you want to learn more. I highly recommend to give it a read. But basically, rather than doing this summation, the Prophet paper suggests to fit this big indicator matrix A. And this is a matrix of size time steps by size change points. And it basically has a 1 for each change point that has already occurred at a certain time. So it's just a big matrix of zeros and ones. And to model then the trend point at a certain time, you can basically take the initial growth and multiply this matrix A, this indicator matrix, with the learned matrix delta. So this matrix delta with the change points is the thing that we're actually going to try and fit. And we multiply that with time. And if we just take this left part, that doesn't give a continuous trend because there's step changes in these growth changes. So in order to then make it continuous again, they introduce this offset term. With like an initial intercept, this is also a learnable parameter, this m, and then you have plus a times minus st to basically offset the change that the step function is going to make. So what I would now like to do, if I can find the new share button, to sort of give a better idea of what this does, is show you this this Streamlit, the small little Streamlit app that I made. So here we see basically the same formulation that we had on the slides for the entire model and also for the linear trend. And what we have on the left side here in this sidebar are the learnable parameters of this Prophet model. And so these are different deltas, this initial growth and this intercept term. And it turns out that if you want to write this down in a bit of NumPy, then it's actually quite simple to do the inference part of this model. And what we see is that if we change our initial growth, then sort of our growth is constant for the entire duration, but it's non-zero, which means our trend increases over time. This M, our intercept, we can move it down a bit, and then we see indeed the entire trend just move downwards. And if we want to have an ever increasing growth, we can basically put all of these individual deltas at 1. So we see the growth at each change point making a small step, and the offset making a ever increasingly bigger step to sort of counteract this, this step function to make a nice smooth little trend. Right, so these are our learnable parameters. And the way that Prophet then suggests to learn these is in the Bayesian framework. So Prophet is written in Stan. Stan is a probabilistic programming language that allows you to basically write down, I have some prior belief over my parameters, I have some observed data, this is how my parameters relate to the observed data, please sample posterior distributions for my parameters. So we get sort of fitted distributions of what our parameters could look like. And well, so Prophet is written in Stan. I don't really know Stan all that well, so I decided let's go and rewrite this in PyMC3. So what I'm going to do now is basically load our data and see how we could write up this linear trend part in straight up PyMC code. So let's start with loading our data, and I think I call it time series.csv. Yep. And I'm going to start with just taking the summer 1 product. Right? I just want to fit 1 product at a time for now, just to keep it simple. What I'm going to do next is I'm going to take the value column and I'm going to min-max scale it to make sure that it's nicely between 0 and 1. And I'm going to take the time column and I'm going to make it a date time, just to be sure that it is. And then our data will look something like this. Yeah, so we have basically some data over time with their corresponding values. And then the next thing that we need to do is set up some hyperparameters for our model. So this change point is a hyperparameter. I kind of want to have an array of times that's also min-max scaled, so also between 0 and 1. And then I can basically use both of these things together to make our change points evenly distributed over our entire domain. Using these two, I can come up with this indicator matrix. So this, I kind of want this to be a 2D matrix of size t by s. So I'm gonna first append like just a single dimensional entry to it to make the t data frame or the t matrix 2-dimensional. And whenever it's bigger than s, I'm going to get a true and a false. I'm going to multiply it by 1 to have a nice integer indicator array. Right. So we haven't really done any fitting yet, but this is just all the setup that we need to do. Now to actually go and fit these parameters in PyMC3, we need to work in one of these pm.model context managers. And what we're going to do in here is basically define all the priors and tell PyMC how they relate. So we can in the end call pm.sample to kick off this process called Markov chain Monte Carlo to figure out what the posterior distributions for a parameter space could look like. And I kind of like starting these models at the bottom. So, and at the bottom we start with, okay, what is our observed data actually? And we basically already said that our noise was assumed to be IID. So what we can say is that we're going to have normally distributed data, it's called observations or something, that is distributed around the trend that we're going to try and predict. with some kind of error that we also don't know yet. So that's also something we're going to fit. But we have observed this data. Right? So we're going to say we're observing the DF, these value columns from our data frame, and they should be around this trend with a certain standard deviation. Now we can basically go up a bit and define how these parameters should be, like where these parameters actually come from. Like where does this trend come from and where does this error come from? Well, we don't know the error. And whenever we don't know something in PyMC, we simply make a parameter out of it and we put a prior on it. And in this case, I'm saying the error term is drawn from a half Cauchy prior, which is basically a normal distribution, but with fatter tails, and then only the positive part, because a standard deviation can only be positive. And that's it for our error. And the trend, we can basically just write down the formula that we had also in the Streamlit app. It's the k plus the dot product between A and delta times t plus this initial offset plus the dot product between A and minus S times delta. Right, that's exactly the formulation that we had. And now we're left with a couple of things. We need to define, okay, what is K, what is M, and what is delta? So K was our initial growth, and because everything is standard scaled, we can basically say, well, I'm not sure yet what it is. It can be positive, it can be negative. So let's just draw it from a normal distribution centered around 0, like a standard normal distribution. And something similar, that's something we'll do for this offset, but I'm really not sure how, like, where it starts. So let's make this a wider normal distribution. And then this delta thing, we said we wanted to regularize heavily. So what we'll do is we'll put a Laplacian prior on it. And a Laplacian is sort of like this very steeply peaked distribution. So there's very much weight around 0. And that has the effect that parameters will get drawn to the 0 value and basically make it 0. If you use lasso in linear regression, lasso regularization, that's actually sort of the same thing. Bayesian regression with a Laplace prior is sort of L1 regularization on a regular linear regression model. And these deltas can be much smaller because we kind of say, well, we don't expect our trend to change all that much. So we'll put a rather narrow prior on it. And we also will give it a shape because this delta wasn't just one value, it was a vector. Right? So we can tell PyMC, please fit, in this case, 10 independent Laplacians on it. And the step that we need to do to actually sort of fit this model is called this PM.sample thing. And PM.sample will kick off this process called Markov chain Monte Carlo, specifically with an algorithm called NUTS, no U-turn sampler. And it's sort of this more advanced way of doing the regular Metropolis Hastings. It uses, that's also why PyMC depends on Fiano, and that's why I use the Fiano dot product here, because it uses this gradient information to basically say, okay, where should I go and explore this space? And what you can then do is, well, when this is done fitting, we can ask for what is the trace plot, and that will show us, okay, how did PyMC explore a parameter space and what are sort of reasonable estimates for these different parameters. And while this is fitting, I'll also just write out this, which is some utility functions that I've built on the side for plotting. So I need to basically put in the trace mean, the trace delta, the trace delta, the NP dot mean of trace K, and the NP dot mean of trace M, and I think, right, yeah, I also needed the S. And I have this other thing called trend that needed, I think the DF, yeah, the trend DF. Right, so let's look at this thing first. So we asked PyMC to go and sample this. Let's actually combine this through, make it slightly nicer to read. And we basically see that these are then, so these are the distributions over the parameters that PyMC think makes sense given our model and our observed data. So it thinks the initial growth is sort of around 1, the initial offset is about 0.5, and then there's a bunch of deltas ranging between -4 and 4. The error is actually quite low. And when we then plot how this relates to the actual data, then we see that this is the growth that it thinks makes sense over time. This is the offset that corresponds to it. And then this is the fitted model. And funnily enough, this actually makes some sense. It's definitely not the behavior that we want, because what our model is doing here is using the change points in the trend to fit a seasonal pattern. And this is not something that we can extrapolate, but I mean, it clearly shows that it's able to sort of adjust to our data and fit accordingly. So this is quite nice. We have a linear trend. So the next step is going to be our seasonality. And then I'm gonna swap back to my slides. Right, so this we covered, this we covered, this we covered. Right, Fourier seasonality. So how profit fits the seasonal component of your time series is basically by fitting a series of cosines and sines with different frequencies on your data. And that is called a Fourier series. And basically it's shown that any arbitrary function, if you have an infinite amount of cosines and sines, you can approximate any different function. And this has one major hyperparameter, well, two major hyperparameters. This P, which is the period that you expect your seasonality to be, and this N, which is the number of components of these cosines and sines that you're going to sum together. So this N basically is in the, I always forget it, it's the denominator, no, the numerator of this fraction. So if N increases, the frequency of your cosine and sines waves also increases. And these A of N and this B of N are then the fitted parameters. So we have 2 times N, 2 times big N number of fitted parameters for this model. And what it then looks like is basically like this. So this is some learned weight times our initial cosine, some other weight times our initial sine wave, and those two get summed together. Then we have a higher frequency wave coming through it, added up to it, and another higher frequency sine wave added to it, to finally end up with this major seasonal component. Right, that doesn't look so bad. So let's also try to put this thing in, yeah, this one, right? Yes. So you should see Streamlit now again. Let's see how this works. So we have different, whoops, right, there we go. We have 3 components here, so A0 to A2 and B0 to B2, and we can basically add them together in a bunch of different ways to come up with interesting seasonalities, right? I don't think this one will actually make a lot of sense in most use cases, but who knows? Right. So all these different waves are summed together. It gets added with our trend to get to a final prediction for our series. So let's try to build this in PyMC as well. I'm just going to go back here and add these additional hyperparameters that we need. Let's start with the number of components. That's this order of the Fourier series that we needed. And then we need some kind of function that basically makes the values for the Fourier series, the unweighted values for the Fourier series. I'm going to say this is this function x. It takes t, it takes the periods, and it takes the order. And then small x is 2 times np dot pi times np dot a range of n. I think I'll need brackets on this. Plus 1, right? This is the the
Hi,
numerator.
Matthias. There is
Oh,
a question from Robert.
yeah.
He's asking, can each change point have its own prior parameter or prior distribution?
That's a good question. So in Prophet, no. The default allows you to only set a single prior, but there's nothing really stopping you from doing that differently. If you have a good reason to say, like, it's actually not a bad idea, right? Because you sort of expect that in the beginning of launching a new product, the trend might change more heavily than sort of when it's established. So yeah, makes sense. It's not something I've thought about for time series yet, so currently it's not possible, but it should be relatively straightforward to add. So thanks for that suggestion. Is there another question or?
Oh, not yet.
I'm losing my Zoom bar. That's it. Cool. Right. Where was it? Yeah. So this x of t. Then the final thing that's left is once again do this broadcasting trick for t and divide by the periodicity, and we concatenate these together. The cosine version of it and the sine version of it over x is 1. So this x of t basically gives us a big array of these 6 Fourier components for all time steps. So that's something that we can use inside our model. And then actually the main thing that we need to change is, well, rather than saying that we observe our trend data, is that we observe our predictions. And our predictions are our trend plus our seasonality. And our seasonality is this x of t multiplied with beta. So it's a dot product of this and beta. And beta is then, once again, a learned parameter. So once again, we put a prior on it, 0, 1, and it's a vector. So it's the n components times 2, because cosine and sine get their own weights. And if we now fit this, then we can look at the trace plot when it's done. We can look at the trend data frame when it's done. And I did something similar for the seasonal predictions. So let's start building that part already. It's the seasonal components. I don't get auto-complete. It's time, and then probably the trace data. Once again, over x is 0. And then plot seasonal components, BF and seasonal BF. And that's done. I should be able to say plot all DF, trend DF, seasonal DF. So we see that fitting is not super fast. The sampling process in Markov chain Monte Carlo is generally not as fast as doing just optimization, because it also gives us a different answer. Rather than just saying, I think this is the highest likelihood point, it says this is a distribution of likely values. And just inherently, that's a more costly computation to do. But it also gives us something powerful, which is forecasting uncertainty. And there's something that went wrong here. Right, I need to divide this, this x of t, this needs to be 365.25 divided by the length of t, because this t is scaled. That's gonna make more sense. But it gives us forecasting uncertainty. And if you're gonna make decisions to maybe expand your factory or to do workforce planning, you kind of want to have different scenarios. Like, what is the likelihood that this will actually happen? And what's the range on possible values that it can take? So this forecasting uncertainty is very powerful in that sense. Right, so this is the fitted version of our second model. That makes a lot more sense. We see the trend indeed increases over time. So our trend prediction is kind of gibberish when we compare it to the results. And the same thing happens when we just look at the seasonal part of our decomposition. But actually, when you add them together, it suddenly makes a lot of sense again. And we actually are able to fit our model relatively well. We definitely didn't capture any kind of weekly seasonality because that's not something that we described in our model yet. But you could see that probably like taking these two things and adding a single other parameter vector beta and specifying the seasonality differently, you could add the weekly seasonality effect rather straightforwardly. Let's go back to slides first. Yeah, so this is what we've done. Right, so but before we actually go in and do that, it's worth a bit about discussing like how are we going to formalize this? Because it's nice that we were able to sort of write down these components and that we were be able to write them in PyMC. But not everyone knows PyMC, and needing to write these things from scratch every time for each specific model that you want kind of takes away the speed of iteration that you generally look for when you want to model these kinds of problems. So let's draw some inspiration from two other packages, obviously Prophet, but also the forecast package in R. So what Prophet does is use a Fluent API. And a Fluent API basically means that whenever we call a method on an object, that it returns itself so that we can chain these objects together. So we can start with a Prophet model, add a monthly seasonality, and add a yearly seasonality. And that works relatively fine as long as you're happy with what is in Prophet. But we already saw that we weren't, and that we might want to add different types of seasonalities. We might want to add different ways of combining them, right? We could say, this is the seasonality, but I want to multiply it with a constant 1 or -1 to sort of indicate this co and contra seasonality. And if I wanted to make those changes to Prophet itself, I would have to go into their source code and probably just rebuild the entire thing. And that's not what I wanted. So the other option would be to do basically what Forecast does in R, and that is rely on this formula syntax, or in Python we have these patsy strings to specify different models with different relationships. And that's already much more what I'm looking for, because you could imagine here, we can say, well, I want to have the trend plus the seasonality, but I could in the very same way say, I want to have the trend times a seasonality to get a multiplicative effect. Or I want the trend plus open bracket indicator times seasonality close bracket. And that's already much more what I want. Except that this relies heavily on non-standard evaluation in R, and that's just something that we don't have in Python. And I also don't want to have some kind of custom built string parser for this, because then it's once again very hard to extend to different classes. My aim with time series is that everyone can go in and write a custom component without needing to touch the core time series codebase. So the solution I came up with was to use an expression tree. Basically, everything in the tree is a node, and every node in and of itself is a time series model. So a linear trend is a time series model, a Fourier seasonality is a time series model. But this multiplication here is also a time series model, namely a multiplicative time series. And this addition here is an additive time series model. And these have left and right components and can sort of recursively go down in the tree to get the things out that I want to get out from them. So let's start with a sort of small numerical example, just to drive the point home, like what do I actually mean and how would this look like in Python? I have this class called node here, and it has two methods, dunder_add and dunder_mul. And for those of you who don't know, these correspond to the plus operator and the times operator when we write regular Python code. So dunder_add takes two things, self and other, the left and the right part, and it returns an add node with the left part set to self and the right part set to other. And the same thing goes for the multiplication node. It also has a left and a right part. And the only thing that's actually different between the two is that when we ask for their values, that the add node takes the left value plus the right value, and the mul node takes the left value times the right value. Also, the string representations are slightly different, but that's just syntax. That's just for us to look at. We also have this one number class, which is also an instance of node, and it just represents a number, and its value is simply s.n, the value that it was initialized with. And what we can now do is we can define a computation, which is number 5, 6 plus 7 times the number 8. And because operator precedence in Python just takes the regular math operator precedence, it will first multiply 7 and 8 and then add 5 and 6 to it to get to the number 67. But what I now also can do is I can apply brackets in arbitrary places. So I can say, well, first please add the numbers 5, 6, and 7 together, and then multiply it with the number 8. And with some imagination, you can probably already see where I'm going with this, because I can now relatively straightforwardly start writing on a class-based approach to solve this same problem. I can write a time series model class, which is basically the node in the example that we saw before. And this is therefore where this add will live, self other, and it's going to return an additive time series object with self and other as its components. And the mul method of self and other is going to return a multiplicative time series object of self and other. And then the other thing that we kind of need on this is a fit method. And that takes self, the time, and the values that we want to fit for. And in this fit method, I'm gonna make a PyMC model, and I'm gonna recursively ask myself what my model definition is. I'm gonna pass the model, the t, and the y in here, and I'm basically going to say that this is my prediction. And when I have that, I can basically go into this context manager. Once again, say, oh, my error is from a half Cauchy distribution with parameter 0.5, and my observed data is normally distributed. Run my prediction. So my mu is prediction, my sigma is error. And I have observed data, which is y. And we can do pm.sample. So that would be pm.sample. I think I had like tune is 200, draws is 200, course is 4, chains is 4, and we store that on self.trace. Right, so this is basically all that's there for our time series model. Then we need to write our multiplicative time series, which is a time series model. So it inherits from it, and it has an init method. Self, left, and right. Self.left is L, self.right is R. And the definition of this thing, so this takes self, model, T, and Y, is basically the left definition model T and Y times the right definition of model T and Y. And I can do the same thing for an additive time series, but then with a plus sign in the middle. The actual components we still also need to add. So we have this linear, I should make this classes, not functions. That's very wrong. So the linear trend is also a time series model. And in its init, it can basically take all the hyperparameters that are relevant for the linear trend, which is the number of change points. It also needs to have a definition, self-model TMY. And for this definition, we can basically copy a bunch of this stuff. So the K, the M, and the delta, and how we compute the trend. This all needs to happen inside this model context. And the trend needs to be returned at the end. And then what we're missing is still this A and this S. So let's also copy those. This needs to be self.endChangePoint, and then that's, I think, it. This also needs to be self.endChangePoint. Someone notices a typo somewhere, please let me know, because looking for them can be extremely tough when life gotten like this. In the same vein, I'm going to make a Fourier seasonality component. So it's also a time series model. It also has a dunder in it, and it takes the P and the N, so this is the period and the order. I'm going to store those here as well. Then I had this, right, I need this X thing in here. And I need this bit. Right, I think that's it. So inside this Fourier seasonality, I can also make a definition, self-model TMY. And open our model context manager. Make this, put in this beta with self.endComponents. And we'll use self.x of t and beta. Right, this can be self.p. And we need to return seasonality at the end of this. No syntax errors, that's always a good start. Because what we can now do is say, well, give me a model that's a linear trend with 10 change points and add a Fourier seasonality to this. Seasonality to this with n equals 3 and p equals 365.25. And call model.fit. Did I save the trend on self? Yep, nice. Model.fit on the on t and the value. Right, I'm doing something wrong. Missing a. Oh, right, this needs to be self.model. And then Fourier seasonality has no, this is just n. And then it says it's not subscriptable. Fourier seasonality object is not subscriptable. Right, what do I have? Right, this needs self. And then we see another nicely sampling bit of code. Let's take our plotting code from up here, see if it produces the same results. But rather than putting the trace, I'll put in the model trace. Right, exactly the same. That's a good sign. So basically, we've changed this this version of our code where we just have everything written in this one step, and we turned it into a nice bit of object-oriented code that's both open for extension, right? Because I can basically everything I need to do to make a new component is write a class with a definition in there. But it's also closed for modification, because if I want to add a different component, I once again only have to create a class and I can directly use it. I don't need to register it somewhere. doesn't need to be part of some kind of parser or some kind of other grammar or method chain. I can just straight away start using it as long as I have this definition. And this is why I think that this way of writing down an API for this is much more powerful, because, well, as I said, you can basically just replace the plus by a times, and we'll get a horrendous prediction, because this is obviously not a multiplicative seasonality problem, but it does just sample and it does just work without any real issues. So let's go back to the slides, because I'm not going to bore you with waiting for the results, because actually fitting this for 5 models does take a bit of time. But the result is this. So we see some things that we expect, and we see some things that are horrendously wrong. So our red product was indeed decreasing over time. There's a quite clear seasonal component to it. That's very much shared with the blue line. The blue line indeed has a trend that starts to break around here and goes up quite a bit. But especially these new products, the yellow and the green one, are doing something completely out of whack. And that makes sense. And also, if we look at the individual components, we can see why it does that. Because there's just a lot of flexibility in especially the seasonal part of the model. And because there's not a lot of data, it's just going to try and fit as best as it can, and it's not really constrained by other parts of the history. So you could now say, well, let's give up. We can't really make proper predictions for this. But we can also say that, well, our model is a bit sick. Our model has amnesia, because it's now forgetting everything that it learned from one series when it goes to predict the next one. And that's not a good way to learn about the world. We have some domain knowledge that says these should be related, they should share parameters. And the Bayesian way of thinking offers a really nice approach for this. And this concept is called partial pooling. Let's imagine, for example, that we have 2 sets of points, these purple ones and these orange ones. If we want to estimate the mean of these points, we could estimate them as totally separate, as unpooled parameters, where we just, well, we take the purple points, get their mean, and we take the orange points and get their mean. But you probably see that the orange one has more points than the purple one, so you're a bit more certain about this value than this one. You can also take them fully together, put them in one single group, and then you get a pooled estimate. And then you say, oh, I'm pretty sure the mean of these points is somewhere in between them. But that's also not great, right? We do want to be able to say that our products are different. They don't have to be exactly the same, but they're not completely different either. So what do you have in between? Well, partial pooled. And partial pooling basically says, I'm going to take my original measurements and I'm going to sort of shrink the parameter estimates towards the global mean in this case, or what I would have estimated if I would have estimated them all together. So we're allowed to deviate from it, and the extent to which we deviate from it is determined by the amount of evidence that we have that they deviate from it. So because we have less evidence that the purple points deviate from pooled, because there's just less observations, we see that the partial pooled estimate is much closer to our fully pooled estimate. Whereas for the orange points, we have a bunch of more data points, so our partial pooled estimate is still very close to our unpooled estimate. And this concept is called shrinkage, because it basically shrinks our estimates towards the global mean, towards our pooled estimates. I'm actually, in the interest of time, going to skip through these 2 slides. Please show you, I'm also not going to build it, I'm going to just directly show you how the code then goes and looks. So I modified this case, and you see that the one parameter that we're trying to estimate is this beta. And if the pool type is not partial pooling, then we see that the definition is basically the same as what we had. And it's a normally distributed variable of a shape n groups n-params, and n-params is the order, or twice the order. And that basically means that if there's complete pooling, n groups will be set to 1, and if there's completely non-pooled, then n groups is set to the amount of groups that we have. The interesting part, though, happens in this partial pooling. So we still have this beta variable, but it's now a deterministic variable, and it's actually the mu beta plus the offset beta times the sigma beta. And these mu beta and the sigma beta are globally estimated parameters. And these are these two, and we see that they only have a shape for the number of components that we have, not a shape for the amount of groups that we have. So these are globally estimated for all our series. And the only thing that we have separate for each series is this offset beta. It's n groups by n params. So offset beta basically estimates how far away from the global mean in terms of the amount of standard deviations that it has is each individual time series' beta vector. And that is that partial pooling. And we see basically exactly the same with our linear trend. We needed to estimate this k, and we needed to estimate the delta, so the initial growth and the growth changes. I basically decided to make the m always, that actually should be dedented here. The m is never shared. I thought that didn't really make sense for an intercept. But we once again have a sigma and an offset. We don't have a mean here because I kind of assumed that the mean would always be 0. It's like, how far away is it from 0 for each group? And basically, that allows us to write our final model for our data down like this. So our partial pooled model is a linear trend with 10 change points plus a constant between -1 and 1 times the yearly seasonality, which is partial pooled. So we don't have a single seasonality, but they will be drawn together a bit. And then there is this indicator, this constant thing, that's basically just a value between -1 and 1 to say, is this a co-seasonal or a contra-seasonal product? We then take a weekly seasonality, that's this thing, and we add it to it in the end. And we call fit to actually go and fit the entire thing. And then our result looks like this. And when we start comparing it to our unpooled estimate, we see that especially for the observations, for the series where we didn't have a lot of data, so the gray one a bit, but in much bigger effect, the green and the yellow one, we just get much more sensible predictions. Because we basically say, please treat them as if they have some kind of parameters shared with the rest of our series, for which we do have a lot of data. If we look at the individual components, we see everything also makes a lot of sense here. The trend is very much the same as that it was, but our seasonality is basically completely agreed upon. And that is because this scaling allows us to deviate nicely from it. And you might even go a step further here and say, well, the seasonality should maybe just be fully pooled at this point. Might even be better. Fourier seasonality, or the weekly seasonality, sorry, also seems to be a bit tighter. We obviously see that they're not the same. There's different scales effects, but the overall pattern of like day 2 being more positive and day 5 being very negative and day 4 seems to hold in all the different series. That's also because that's how we constructed the model, where we say, well, please shrink them together. We think all the weekly seasonalities should be relatively similar. Right, so all of this is open source. It's all on my GitHub, github.com/mbrown/timeseries, but it's not really ready for like primetime production usage yet. The fitting process works well, but something that's still like very much in flux is the predictions API. The way that it currently works is just not sufficient. It's very hard to add, well, it's very easy to add additional regressors like the events and like promotions and stuff, but it's very hard to get them in the predictions API at the moment. So I need to basically redo part of that. And when that's done, I think the core is mostly there, and I'm going to push it to PyPI and hope people will start using it. And then we can add basically whatever we need at that point, right? If we need other seasonality functions like radial basis functions, well, we can. If we need the saturating growth that Prophet described, we can. If we want to add like mini Gaussian processes for holiday effects, sure, why not? And that's sort of what my entire goal is with this, to build almost like a domain-specific language that makes it very easy to basically plug and play with different blocks for time series modeling. I hope you enjoyed it, and I'll gladly take any questions if they are there.
Thank you. This was super helpful and definitely interesting. We have a question. Are these results for each case, for the case when we are creating a model for each time series?
Right. So the bottom one here is indeed completely separate models for each individual time series. So this is the completely unpooled example, the bottom chart here. And the top chart here is with this partial pooling. So I estimate them all together. I allow parameters to deviate, but I do estimate them all together. Yeah.
Another question is, how does your model work with other time series datasets?
Right. So define what other time series datasets means, because that's a very broad topic. Are you going to predict stock market prices with this? No, not at all. There's no seasonality in there. And in general, predicting stock markets is a bad idea. So that's not what I'm focusing on anyway. Brainwaves, same thing. That's also time series, but I don't think there's a lot of seasonality in brainwaves. So probably I wouldn't do this for that kind of data either. I've been sort of toying around in my spare time with another data set with Wikipedia page views. And that does seem to work quite well. Right? Because Wikipedia page views also have this this sort of shared behavior, right? If there's a football club playing, like there's football season, so naturally different football clubs will have more traffic to their pages in football season, for example. There's these holiday effects where people will look for Wikipedia pages for touristic destinations in summer, and in winter those will be different. So you'll have those go and contra seasonal effects. And that does seem to work reasonably well as well. The effect is a bit less pronounced as with this one, and the fitting here is quite a bit easier. So I went with this example for the talk, but it does work for those kinds of data sets. Yeah.
Okay, great. Another question is how to check the performance with this type of modeling, maybe evaluation metrics or information criteria?
I think that's the same as with all other time series models. I personally like just out of sample predictions. So doing rolling forward, rolling window, moving forward cross validation, either in a nested way or not. That does seem to work well for my use cases most of the time. But if you're currently used to using AIC or BIC or something else for your model evaluation, that should work fine for this as well. Yeah.
Another question is, can we add exogenous information that follows the hierarchical structure of the data? For example, dynamic prices for different products, where we would like to have a global parameter for price, but still adopt the individual price for each product.
If I understand you correctly, I think we should be able to do that, because this constant thing, I still need to add a component that says, and you still need to add a regressor that's in the works, but part of that is the problem with the prediction API that I mentioned. But I basically have a regressor component in the works that says regress on a specific column. And that's also possible to estimate that hierarchically. So I think the answer to your question is yes, if I understand it correctly. And if not, let me know.
Or maybe Roberto can answer this question. Okay, there is another question from me personally. The length of the data sets have to be the same, or maybe this model can handle any time series length.
Sorry, the question was, does the length of the data sets have to be the same?
Yeah.
No, they don't. Like, so I chose, I didn't even need to do that. So when we go back to our original data, we actually see that the length of the individual series is already different. For some reason, loading the GIF is really hard. Right. Go back too far. Right, so the length of the individual time series is already different, but it would have also just worked if orange and green or yellow and green have started here, right? There's no issue there. There is this thing, so the trend currently I estimated separately. I basically said, well, all individual series are allowed to have their own trend. So as long as the seasonality is sort of on the same scales for the product, then it's fine if they are completely different lengths or completely different time frames. There's no worry there. Yeah.
Okay, thanks. How would you deal with seasonality in the various of the data?
Yeah, it's a good question. So in terms of the model, it's actually not that hard, because what I did now was just say there is some kind of variance that's constant. That was this error term that I estimated. And it wouldn't be very hard to make this dependent on time in any way, right? We could say that the errors actually follows this same Fourier seasonality, and increase indeed at certain points and decrease at other points. The main thing that I was struggling with is where to put this in the API at this point. So you could probably, like, you can't just add it as a component, right? Because that's not what that noise is. You can't really estimate it in that sense. So I would need some kind of marker or maybe some kind of other operator to actually say, well, if I do like a bar, maybe like a bitwise OR that sort of indicates that is how the variance should be estimated. But I wasn't really too pleased with how that looked yet. So conceptually definitely possible, but still would need to be built. And if you have any suggestions on how an API could look for that, I'm super open to suggestions, because that's indeed would be a very nice addition to this library. Okay,
great. So we definitely want to give a huge thank you to Matthias. This was awesome and super helpful. Thank you.
You're welcome.
Please follow us on Twitter for details about the upcoming talks to get notified. And with that, again, thank you, Matthias. And thanks to everyone for joining.
Yeah, thanks for hosting this event. Best of luck with all the additional webinars coming up. And yeah, if anyone wants to get in touch, I'm always available on like LinkedIn or Twitter, and I'm happy to engage with you on this, because I enjoy this library. I enjoy working on it, and if anyone has suggestion, please come ahead. Yeah.
Nice. Thank you so much.
Okay, great. Thank you.
Thank you, and hopefully see you next time. We're at PyData Global.
Yeah, sure.
Of course.
Thank you. Bye bye.